A very good morning to Dr. David and my friends and me, Chong. My matrix number is B0822100041, and with my group mate Muhammad Hasyim, we are going to present our group assignment for digital signals processing, which is we need to find any one lab from lab 1 to lab 5 that is interesting to us, and we need to expand the labs, and then we need to expand the lab by adding some new procedure to it, new ideas. Then we need to expand the new ideas through the our modifications. Okay, Dr. David, this is our team members for this group assignments. We have Muhammad Hashim, bin Muhammad Rafee, and me, Chong. Okay, this is our table of content, which is introductions, team overview, selection of lab sections, original sections, new addition to the sections, demonstrate and applications, challenges and solutions, and finally conclusions. And I'm going to present the introductions and the explain how the labs we did, and the modification to the labs, the adding sections to the labs, and others details of our presentations. And Muhammad Hashim will going to explain the simulations for the MATLAB. Okay, this is the overview of digital signal processing. So what is digital signal processing? Digital signal processing, DSP, refers to a processing of signal by digital systems like personal computers, PCs, and system designed using digital integrated circuit ICs, microprocessors, and microcontroller. So this is a block diagram of the basic component of a digital system. We have input analog signals. Then we go through the analog to digital converters, then it will becomes input digital signals and then go through digital systems, and output digital system will go through the digital to analog converters before we get an output analog signal back. So these are basic components of digital system and the block diagram. So how is the importance of DSP, digital signal processing, in our real life applications? So common DSP applications include audio and speech processing, image and video processing, medical signal analysis, radar and sonar system, communication system, and many more. So digital signal processing is very important to us because every day all the gadget, all the phones, all the electronics systems is used the DSP as a applications to us. So the purpose of digital signal processing is to enhance, analyze, and transform signals in a way that makes them more useful and interpretable for various applications. So it's very important in our real life. What is filter design in MATLAB? Digital filters are central to almost every signal processing system. Filters eliminate unwanted artifacts from signals to enhance their quality and prepare them for further processing. Digital filters are used in a variety of signal processing tasks, including outliers and noise removal, waveform shaping, signal smoothing, and signal recovery. Because if the our noise, the sounds, we have very noise at the backgrounds. Like I'm talking about some speech, then the background we have some noise disturbance. So we use filter to filter out the noise, which is in high frequency sometimes, mostly in high frequency. Then it will have more smoother speech. Then we can more clear to hear the what people saying about. So we use filter to let the signals more smooth. So me and my team members decided to use select the LAB-5 as our assignments lab. So we need to demonstrate the LAB-5 and shows how LAB-5 work, and then we need to modify it. We by changing the frequency, the stop band and pass band frequency of the filters. Then we also change the type of filters to another type. So let's us see about how it is working. So LAB 5, what are we doing in LAB 5? Summary from LAB 5. The objective of LAB 5 is to aim to teach students that us the fundamental steps of identifying signal components before designing filters, understanding the function of various filters, and applying these filters to meet specific requirements. The primary goal is to remove noise from a signal and enhance its qualities. Let the signals more smoother, less disturbance, less noise, make the sounds, makes the signal more clear. So first of all, the task one of the LAB-5 is we need to draw the block diagrams simulating that's as shown in the diagrams, and without any filtering, the raw signals, which might increase various forms of noise, is directly fed to the scopes, spectrum analyzer, and speakers. So this setup helps visualize and understand the characteristics of unfiltered signals in both time and frequency domains, as well as perceive its audibly. Filters are typically used to clean up such signals by removing unwanted noise components before they are analyzed or output. So without the filters, we can see that from the results of the task one, the noise, the people is talking, and the background have many noise. So it disturbs the people is talking. We cannot hear the sound clearly. So this is the code we write in task 2. Later we need to insert these parameters to the filter in task 3 because in task 3 we need to add the filters. So this is the code, the MATLAB code, which is function ht equal to my low pass 1, which means that we have a low pass filters. So it creates a low pass filter specification object. The FST specify the design parameter is the orders. Passband edge frequency is the FP. Stopband edge frequency is the FST. Passband ripple FP in dBs and the stopband attenuation ST in dB. So the passband edge equal to 4,000 hertz means that the passband edge frequency is 4,000 hertz and the stopband hertz is 5,000 hertz, which is the stopband edge. And our pass ripple is 0.1 dB and stop pass attenuation is 50 dB. 22050 is the sampling frequency, which is 2050 Hz. Assuming this is the intended sampling rate. And HD is the design, D butter is the Butterworth filters, and the FVTOL means that visualize the frequencies responding of the digital filter HDs using the filter visualizer tool. So this is the summarize of the code that we need to insert this parameter to the filters. So in task 3, we insert a backward filters to the Simulink block diagrams. So what is the function of the backward filter is to reduce the noise by selectively attenuating unwanted frequency based on its adjustable parameters and efficient processing capabilities. Its effectiveness in noise reduction depends on how well its parameters are tuned to match the characteristic of the noise in the input signals. So after we insert the parameters just now, we can see that the output signal is more clear without noise, and we can hear the people speaking very clearly. So for task 4, we change the backward filters to notch filters. So a notch filters, also known as a band stop or band reject filters, which is designed to attenuate or reject a narrow band of frequency while allowing frequency outside this range pass through it. But by using a notch filter in Simulink, we can effectively remove specific unwanted frequency components from our signals, improving the overall signal quality for further processing or analysis. The visual representations. So here's the examples of simple similar model with a notch filters shown in the diagrams. From the multimedia file block is used to read the input signals, and discrete filter block is configured as a notch filter with specific coefficients. For the scope block is to visualize the filter's signal, and spectral analyzer block is to observe the frequency domain representations and confirms the attenuations of the specific frequency. Okay, here's now is the next task, which is design filter task. We need to design the filter by our own. We need to set the pass bands, stop bands, and the sampling frequencies. Then we get the outputs of the filter. So here's the parameter we set for the design filter, which is low pass filter, and then we set FIR, we set the minimum orders, and then we set the sampling frequencies 32,050 hertz, and the passband is 4,000, and the stop band is 5,000 hertz. And the units dB, which is the passband dB, is 1 dB, and the pass stop dB is 50 dB. So why use FIR filter to reduce high frequency noise? Because stable and reliable. FIR filters are always stable and won't produce unexpected results. Preserved signal shapes, they can be designed to delay all parts of the signal equally, which means they won't distort the shape of the signal. The flexible design for the FIR filter, we can easily create filters with the exact characteristics we need. And FIR filters are easy to use, especially in digital system, and work fixed efficiently. Okay, after done with the LAB-5, now we do the assignments which expand the LAB-5 with different ideas. We changing the parameters for the design filters. So as we can you can see from the pictures, we change the parameters to another two's parameters, so we get different results for the output signals. So we change the sampling frequencies to 200,000 and the pass band frequency to 12,000 and the stop band frequency to 14,000. We can see that the output signal is compressed, and after that we change again the sampling frequency to 500,000 hertz and the passband frequency to 4,000 hertz and stop band frequency to 5,000 hertz. We can see that the result is most compressed, the output signals. So this is the parameter that we change, we modify, we expand the different parameters for the design filters. After that, we change the filter to different type of filters which are available in Simulink, which is COM filter. A COM filter reduces noises by creating a periodic notches in the frequency spectrums that align with the frequencies of the periodic noise components. By attenuating these specific frequencies, the COM filters effectively reduce the amplitude of the noise and resulting in a clearer output signal. So why we change the notch filters to COM filters? What is the difference between them? Which is COM filters is multiple notch or peaks. The frequency response of a COM filter consists of a series of regularly spaced notch or peaks, which occur in the integral multiples of the inverse of the delay periods. And the notch or the peaks repeats periodically across the frequency spectrums. While, in the other hand, for the notch filters, each single notch only, which the frequencies response of the notch filter has single dips and narrow notch at the specific frequencies. And the design to attenuate only a very narrow band of the frequency around a central frequency for the notch filters and leaving other frequencies largely unaffected. So this is the difference between notch filter and COM filter. After that, we changed the filter to another type of filter, which is elliptical filter. What is elliptical filters? Elliptic filter, also known as curved filter, which combines the characteristic of both Butterworth and Chebyshev filters, providing a steeper roll off and sharper cut off. In simple terms, an elliptic filters reduce noise by precisely blocking unwanted frequencies while letting through the frequencies you want to keep. It does this by creating a sharp boundary between the allowed frequencies, which is the passband, and the blocked frequency, which is the stop bands. And this sharp cutoff helps to clean up the signal by removing noise that doesn't belong to the signal of the interest. Additionally, it minimizes any wealthy distortion, which is the ripple in the signal itself, and ensuring that the filter signals remain as close to the original as possible while effectively reducing noise. So this is a summary of the tasks and activities we did in LAB 5, which identifying the signal and noise components, import the visualize and import and visualize the signals, which is the mystery 61.wave files in the MATLAB and Simulink, characterize the signal and noise components. We select the filter configurations based on the identified components, decides on using a low pass filter or a notch pass filter or the band reject or band stop filters. Specifications for the filter include parameters like we set the passband age, passband ripple, stopband attenuation, notch filters, and bandwidth. For the filter design implementations, we use MATLAB functions or simulating blocks to design and visualize the filter responses. We implement filter using different methods such as we use backwards filter blocks, digital filter design blocks, and the filter realization visit. Compare the effectiveness of a low pass and a notch filters in removing noise from the signal. Result and discussions. The labs demonstrated practical techniques for designing digital filters to clean up the signals. Students gain experience in visualizing and characterizing signals, selecting the appropriate filters, and applying this filter using MATLAB and Simulink. The flexibility of the filter design in MATLAB of Simulink allow for easy adjustment and visualizations of the filter effects on the field signals. The practical approach reinforced the understanding of digital signals processing concepts, especially the importance of the filter specifications. So this is the result and discussion we get from this lab, the five. So this is the additions parts from us, which the application of the LAB-5 in our real life. For example, the applications in our real life, we use the filter as in the communication systems, in which signal cleaning and channels separations. For the signal cleanings, filters are used in the communication system to remove noise and interference from signal received over various channels, ensuring the clear transmission of the data we transmit from the transmitter to the receivers. And the channel separations. We use filters to separate different channels, communication channels in systems like mobile phones and radio broadcasting. We separate them so that we do not have the distortion or the interference between the different channels.
So hello and hi. Today I want to present the MATLAB code. So for the first line, this line is defines a function named as low pass one. For the second line, this is specify the filter design parameters. So the FP is the pass band, FST is the stop band, and the AP is the ripple in decibel, and ST is the stop band attenuation, and the value that is represent the 4000, 5000, 0.1, and 50 are corresponding to the values for the FP, FST, AP, and AST. So the 22050, this value is the sampling frequency of the signal. So the third line is basically design the actual filter using the specification in D. Uses a Butterworth filter. For the FT tool that provide visual represent of the filter. If we run this code, it will represent the magnetic phase. So from this magnetic response, we know that it's appear the low pass filter. So this task we did on our previous lab. So in this multimedia file, we need to put our audio file actually. So here I want to import the file from the previous file. So this is the mixed signal we put on the block parameter. So this part will be read the signal and display the visualize the original signal. How the signals is produced by the visualizer, is this having a noise or not? So if you look here, if you run the signals, so have a look.
The discrete Fourier transform of a real
So
valued
as
signal is conjugate symmetric. The discrete Fourier transform of a real valued signal is conjugate symmetric.
so as you can hear that they have some noise that disturbed by the high frequency. So we need to so for the next task, we using the notch filter. So this notch filter, known as a band stop or band reject filter, is designed to attenuate meaning that to reduce the amplitude of a specific range of frequency and allowing the frequency outside this range to pass through. So it will allow the frequency at the specific range only. This type of frequency is particularly useful for eliminating unwanted frequencies. The notch filter also having the same objective to remove, same as the previous filter or others filter, to reduce the noise such as power line interference, so each other. So here I put the audio file again and have a look the output.
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric.
So what we can see here is have totally removed the high frequency because of using the notch filter. So if we use the variable bandwidth IIR, this is basically using the same methods as the IIR filter. The IIR filter is designed using the elliptical method. This IIR filter is tuned using IIR spectral transformation based on all pass filter. So if I use this filter in this block parameters, the having a we can choose the low pass, high pass, band pass, and band stop. So here we selecting the low pass and the IIR filter choosing the range of certain filter order, and we input the filter pass frequency, pass ripple dB, stop band attenuation as we input in low pass coded low pass code, that we input the this all parameters and we just apply it, and if we run this, so we heard that they are also having no high frequency or and allowing only the low pass frequency. Then the output will be no noise and will be shuttering a bit because of these parameters, and we need to change these parameters to meet the right requirement to got no smooth voice input signals. So for the digital filter designs, we can use this filter designer to perform a low pass response type. So here I choose the low pass and FIR. The filter order is set to minimum order, and the FS still remain the same value as the lab value. So if we design the filter, it will present the low pass here, and if we run, there are no noise will be here from the input signal. So we need to put the signal here and run into the filter and
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric.
so as you can hear that there are no noise after we having the low pass response type of filter and FIR design method with using the value of the lab. So what happen if we changing the frequency sampling frequency? So it's affecting the filter performance and characteristics actually. And what happened the F frequency pass and frequency stop, if we changing these two values respectively, uh, it can tailor the filter to meet the specific performance and requirement. So it also can be wider, or it will be squished when we changing this filter. So if here we have the 10,000 or something, 10,000, and this is the 7,000. You can see it will start cut off from the 7,000, and the frequency will be down here. So if you start from the 10,000 and ending with the 20,000, it will cut off uh, starting from the 10,000 here. So if let's say it's 5,000 and this is 8,000, it's we starting to cut off from the 5,000 here. It's we starting cut off from the 5,000, and it's a it's we show the low pass filter, and magnitude response will be show that this is the low pass filter. If you run this will be no noise, and
The
it have
discrete
been reduced to
Fourier
high
transform of a
frequency.
real valued signal is conjugate symmetric. The discrete Fourier transform of a real valued signal is conjugate symmetric.
It's still having a noise because of we changing the value. So if we change the value as our lab, or changing values until the noise is being removed, then that's all to cut the high frequency. Here we use the backward low pass filter to reduce the noise. So for our theory for backward filters are popular because they are stable and can be implemented efficiently. They offer good numerical performance, which is crucial for real DSP application. So we as we can see, the result from the filter.
The discrete Fourier transform of a real valued signal is conjugate symmetric. The discrete Fourier transform of a real valued signal is conjugate symmetric.
So here there are many filter designs to cut off the noise. So in our case, we need to cut off the high pass frequency. So that's why we using the low pass, the band pass, the band stop, and the and the notch filter. So next, for our additional, we using the comb filter. So in the comb filter, we can change the quality factor and the frequency constraints. And this comb filter act seems like the Butterworth filter because the algorithm is the same. So here, if we remove this notch and replacing with the comb filter, it's actually removing the noise from the input signal. So have a look.
The discrete Fourier transform of a real valued signal is conjugate symmetric. The discrete Fourier transform of a real valued signal is conjugate symmetric.
So yeah, this comb filter is actually uh, removing the noise respectively.
So in conclusions, filters are essential tools in signal processing for cleaning and separating signals. They help isolate specific frequency components and remove unwanted noise. The key filters types include low pass filters, high pass filter, band pass filter, and band stop filters. For the low pass filter, the function is to remove the high frequency noise, which only allow the low frequency to pass through it. And the high pass filter is remove low frequency noise, which only pass the high frequency signals. And the band pass filter will isolate a specific frequency range to allow the frequency to transmit, which only a specific range of the frequency that allow to transmit. And the bandstop filter is eliminate a specific frequency range, which we don't want any range of the frequency. We just reject it. So using our filters, we can achieve tasks like denoising signals and performing channel separation. For example, bandpass filters can isolate individual frequency components from a composite signals, allowing us to analyze each components separately. Filters enhance the clarity and the usability of signals in various applications, from audio processing to biomedical signal analysis. So that's all for our group assignment presentations. Thank you.